already answered that.
All right, the quiz on chapter 5 on Thursday. So, any questions?
Don't we have a lab due on Thursday, and then we have master set number 6 due on Thursday as well?
Good times. Do you want to propose something?
Yes, I think we should move at least one of those to next week. I don't care which one, but just one. Assign them to next week. And I don't think anyone in the class would say no to that.
So which one do we move?
Lab, actually, let the class vote, you know?
Yep. So still with the quiz on Thursday. So I guess master set 6 pushed off till the Thursday after spring break.
Yeah.
Sure.
All right, so let's go to week, master set 6 or centripetal motion lab. All right, if you don't care, then I guess you don't vote. Pushing master set 6 off. That's 2.
Okay.
Oh, more hands popped up? Let's try that again.
I wasn't even aware of it today.
Okay, master's at 6, postponed a week. That's 4. Centripetal motion lab, postponed a week. And that's 5. Let democracy rule. Centripetal motion lab. All right, so any questions on chapter 5? We'll just start out with that.
Can it be like on the problems, like one of the homework problems?
Yes.
So I don't got my textbook with me, but I think it was 41. It was drawn with like a force diagram and like 2 masses hanging from a pulley.
Yes. Atwood's machine.
So I was kind of confused because I was looking through the solution, I guess, how to do it on the the answer key, right? But I got like, I think it was like FT minus GT over the masses, but I got them added together.
All right, well, let's take it step by step here. So we got mass 1, mass 2, and they give us some details. That's mass 1, mass 2. This is problem 41. Let's see, 15.93 kilograms and 10.45 kilograms. Oh. Just recognize that I drew it backwards. Their mass 1 and mass 2 are on the opposite sides. But that is mass 1 and mass 2. So first off, just conceptually, we assume that this pulley is being held up by something. They throw a ceiling into it, so I guess. So we assume that the ceiling is being held up by something. Which way is this thing going to move?
Towards the left.
Okay. So just gut instinct, it's going to go this way. So that's going to fall and that's going to rise. Force diagram, we have basically mass 1, mass 2, rope, and then pulley with ceiling. Let's take the steps. F-tong. What forces are there?
Wait,
I heard weight acting on.
both of them, M1 and 2.
All right. So I have weight 1, weight 2. We don't. The ground is partially irrelevant here, but for completeness. And you could put in weight of pulley here, or ceiling, or whatever subscript you want, since the pulley ceiling is all one thing. Right, that's done.
Tension from on both ends of the rope to the masses.
All right, so I have a tension here, tension here. There's one pair, and the other pair, tension here,
I have a question.
tension here.
So,
Yes.
whenever there's contact between the rope and the mass, is there not normal force?
Oh, at this connection point here,
Yeah.
how is the rope attached to the mass?
Well, if there's contact, isn't there always a normal force that's exerted
In which direction of the normal force then?
perpendicular to the contact?
Yes, but, okay, so if the rope is sort of embedded in there, then the normal force is gonna be pointing horizontally. If it's connected to an eye hook, then there is a normal force acting up on the eye hook and down on the rope. We don't know, and so that's getting bundled into tension.
Okay.
So,
Tension accounts for that.
yeah, so some have claimed that tension doesn't really exist, and yeah, tension is really some other type of force, but we don't know how it's connected, so we're just gonna call it tension. All right, any other questions up to here? All right, so, tension, done. What else?
Normal force on the pulling the rope.
Yep. So something's holding that rope up. Sorry, normal force. So Y and Y. That's the only contact we have going. Any friction?
Is that an ideal rope?
Yes.
Frictionless?
Yes. So none.
And there's no other.
All right. So that's what we have. Direction of acceleration, we've already sort of identified that. This one is going to accelerate downwards, and this is going to accelerate upwards, assuming it starts at rest. Actually, whether it starts at rest or not, that's the direction of acceleration. Coordinate system, or coordinate axes. What's positive?
Oh, acceleration.
You said to the right?
Down?
Oh, down? Oh. So you want to make down positive? For both of them?
Alright, guess you would split it up. You could split it up.
I would recommend it. You don't have to, but it gets tricky here. If you're going to say down is positive on this one, then recognize your acceleration is going in the negative direction. So we'll make that positive and that positive. We can give it a hat label if we want. We can call that I hat 1 and I hat 2. But since it's a one-dimensional problem, we can just get away with positive. Do we need to decompose anything?
No, but I have a question.
Yes.
So like, I think when I did it, I gave them the same coordinate, but you said something about you have to make the second one like flip it because the acceleration is going the opposite direction.
Right.
So, what do you mean, like?
All right, so let's get the equations of motion, and then I'll just do a sidebar about if we had chosen the same direction for positive, what that would look like.
Okay.
By M1 and M2, what's the red things? Nadia, I have the one stereo, that one.
What is this is indicating that the acceleration is down.
That's an
That's an A.
Okay.
All right, so nothing to decompose, and so equations of motion. There's our template right there. How many equations of motion are we going to have? All right, let's do the one or two. Pick one. Somebody tell me.
W1 minus F of T plus F of T, or wait.
You're only looking at when you're doing that. You just look at the forces acting on that object.
is equal to MA.
Thank you. And then Not the way we have it set up.
Yeah. Sorry, negative W2,
Okay.
if you want to do it that way, and then it would be plus tension F2 equals M2A.
All right. So a side note here, if we had picked the same direction, so both being positive, well, this acceleration here is in the positive direction. This acceleration here is still up, but I guess decide. So if we had said down was positive, let's do it that way for both of them. The first equation doesn't change. The second equation would become, well, W2 minus FT, that because they're now in the, that's now in the positive and that's in the negative direction, is equal to M2 times negative A. That's where the negative would come in, because the acceleration, the vector is in the negative direction, and so we got to somehow acknowledge that negative. And then if you multiply the whole thing through by -1, you just get this. Any questions about what I have in purple here?
But you always want acceleration to be positive?
Not always, but you do need to keep track of recognizing that they're accelerating in opposite directions, and you need to take that into account somehow. Originally, my preference is to pick my coordinate system so the acceleration is a positive number, but you don't have to. All right, so I think they wanted to find tension and acceleration. So substitution next.
You can combine both equations.
Before we do that, do we have any other formulas, separate formulas for anything that we have here?
Wait,
And what's the formula for weight?
MG.
All right, so this is M1G, and this would be M2G. So when we add them together, we get M1G minus M2G equals M1A plus M2A. And then depending on, I guess, you're solving for acceleration. So this is equal to M1 plus M2 times A. And then divide both sides by the total mass. And so my acceleration becomes M1G minus M2G divided by M1 plus M2.
Is that an actual equation? Because I feel like that shows up a lot.
Yeah, it's a classic early problem in doing this stuff, and so that's why it seems to show up a lot. It's not one that I would necessarily commit to memory. So if you plug and chug, you can then find the acceleration. Once you have acceleration, well, you've got two equations from which to choose. Pick one and solve for tension. And I guess, Enrique, you were the one who started this, right? Do you want to go through with the numbers, or are you good to go at this point, or?
I think I'm good with that.
Okay. Any other questions on problem 41 from chapter 5? All right, any other questions from chapter 5?
I'm not actually sure if it's chapter 5 or chapter 6, but how do you find like which direction to sign and which direction to fix on whenever you're?
It depends upon the situation.
Well, I mean, like which angle do you use? Because like if there's a box like going down a ramp and there's weight, do you use the angle like on this side or that side?
A couple ways to interpret that. All right, so we've got a side marker. and weight is acting down on the box. And so you're breaking that up into those components right there.
Yeah.
So the question is,
Or like which angle would you use?
typically on a ramp problem, this is the angle you're given, or that's the angle you're asked to find.
Okay.
And so typically it's that one. It doesn't have to be, but I do know that this angle here and this angle here are the same. So if instead you're given this angle up here, I'll just call it phi, and then that'd be phi. So the down the ramp would be the weight times the sine of that angle or the cosine of that angle.
Yeah, that makes sense.
Does that answer?
I think so.
Okay. Other questions from chapter 5? Okay. I don't think I did the pseudo derivation of Kepler's third law yet. Okay. I have posted a sort of the hardcore derivation of Kepler's laws. That's definitely within your realm of what you have covered in calculus. But this is the quick and dirty version. Assume circular orbit or orbit. And assume mass of the planet is constant. The planet is not blowing up as it's traveling around. It's not picking up any space debris as it travels around. And we start out with, same as before, force diagram. What are the forces acting on the planet?
Centripetal force.
Yes, there will be a centripetal force. However, that's not one of the forces for a force diagram. The centripetal force is going to be a combination of the stuff we've already done. We got F-Tom here.
Weight or gravitational?
That's a better word of it, gravitational force. Why is weight not really appropriate here? Yeah, pretty much. Kyle, what you were going to say? I think. Great minds thinking alike. Yeah, weight really requires a small object right there at a large object. Now, if the Earth spiraled into the sun, at some point you probably could get away with calling it weight. Not that you'd be here to do it, but in theory. What else is acting on the planet?
Centripetal force.
Not centripetal force is not going to be a special force. That the weight will be the centripetal force actually.
Tension? Tension?
Is there a rope or something like that connecting them?
No.
What would the other be? Oh, just guessing?
Yeah, I was just asking.
Well, it's moving. Isn't there velocity?
There is a velocity, but not a force. If the sun suddenly disappeared, what would the Earth do?
It just float away.
Continue.
About 8 minutes later. It always seems kind of creepy. If the sun suddenly exploded, we wouldn't know for a couple of minutes. Then there'd probably be a big flash, and then things would start to get cold. All right, so that's it. That's the entire, there is no tension. There's no friction because we're assuming it's not running into anything. Not that that's necessarily friction. There is no other, or it's not touching anything. So just that. What is the direction of the acceleration of the planet?
Inwards. Inwards to the sun.
Okay, so my acceleration is in that direction at that moment. Let's see, coordinate axes.
Towards the sun, positive.
Okay, so we'll make that the positive direction. Decomposition.
Nothing.
All right, equations of motion. We'll start out with the template again.
FG equals mass of planet times acceleration.
And I'm going to put a little c there just to, again, emphasize the fact that it is centripetal acceleration because we have something traveling in a circle. There is acceleration because the direction is changing. Substitution. We have two different formulas here.
V squared over 4.
All right, for centripetal acceleration, so I got mp v squared over r. And v is the one I want here. It could also be omega squared r, but in this case, I want v squared over r. And obviously, the thing hasn't come in to keep the mask away from my mouth. Still hoping. As one person said, if you could breathe easily, the mask isn't doing its job. All right, gravitational force.
Mass times the acceleration due to gravity.
Yeah. What is the acceleration due to gravity of the Earth around the sun?
9.79.
You know, that's the acceleration due to gravity when you're at the Earth's surface, but that's the acceleration due to gravity of an small object near the surface of the Earth. We're talking Earth with the sun. I doubt it's in there.
No,
I suspect it's not in there.
no, it's not on the front page at least.
All right, so that's the problem with using mg here, because we don't know the acceleration due to gravity of the Earth relative to the sun. Or I guess better wording is the acceleration due to gravity of the sun wherever the Earth is at that moment. So we have to use the general formula. What's the general formula for force due to gravity?
Between 1 and 2 r squared.
Over r squared. All right, so our masses, we have sun here, and we have our planet, and this is the sun to planet distance. Oh, and this r right here is the same distance, sun to planet. So now it's time to solve. We're on the second S. Can we get rid of anything?
Multiply by the radius.
Okay. So that radius is going away, and we'll get rid of one of those. Anything else?
Mass of the planet.
We can divide that out. So in essence, we're multiplying both sides by radius of the orbit over mass of the planet. And so we are now left with a simpler formula that this gravitational constant times the mass of the sun over the radius of the orbit is equal to the speed of the Earth squared relative to the sun. I guess that's another assumption we're making. Assume sun is still. Now, formula for speed.
so we're changing time,
Okay, so what is change in x?
changing position.
Not for speed. That would be velocity. What is change in x?
Distance.
Thank you. Yes. So v is just the distance traveled divided the amount of time. Well, I got this thing traveling in a circle here, so what's the distance? Yeah, what's the formula for circumference?
2 pi r.
And that's the radius of the basically the Earth's orbit, divided by the time. Well, again, I have something in repetitive motion, and so what do we call, what's the word for the time it takes to go around once?
A year.
Okay, I was thinking more generally.
Time period.
What's the time period called in general?
Revolution.
It's in the centripetal motion lab. I think it's the second column of table D2. Marisol asked about it earlier.
Average period.
Period. The capital T. It's the period. So that's the speed of the Earth, and so I'm just going to plug that in here for v. So I have 2 pi times the radius of the orbit over the period squared. So bringing that down, we have this gravitational constant times the mass of the sun. One of these markers is bound to work better. Over that radius, the sun-Earth radius, is equal to 4 pi squared, that radius squared over the period squared. And then, let's get all our constants over on one side. So I have g times mass of the sun over 4 pi squared. When I say constant, what I should have said is take all the things that are not planet specific, and that's equal to the radius cubed over the period squared. So based on this, every single planet in our solar system, and even asteroids, anything going around our sun, if you take the orbital radius cubed and divide by how long it takes to go around squared, you should get a constant. This. Matter of fact, we can take it one step further. We could actually calculate the mass of the sun. The mass of the sun is, pick a planet, we got this r cubed over the period squared times 4 pi squared over g, and we can now have a way of calculating the mass of the sun. And I say let's do it. But before we do it, we'll take a dramatic pause here to see if there are any questions. All right, so wait for the dramatic pose. All right, so the orbit of the Earth, how far are we away from the sun on average? There's the easy answer, and then there's the one you have to look up. What's the easy answer for the distance from the Earth to the sun? Kyle, you look like you're about to say it.
Would be after 365.
What's that?
No. Well, the time period would be what, half of 365.
In terms, I'm just looking for a distance here. I don't want to get into time distance conversions, which is more appropriate at the end of the next semester course. All right, so first off, the period. What's the easy unit for the period of the Earth? It was said earlier. Yeah, a year. All right, so the easy unit is 1 year. The easy unit for the radius, 1 astronomical unit. And if you're dealing with outer space, that's probably a pretty decent one to have. However, it's not really going to help us. We could get the mass of the sun. I think this is a master set 7 problem, where you use these. You come out with really strange units, because you let G be what are called naturalized units. So it's 1, that's 1, that's 1. And so the mass of the sun is 4 pi squared in these bizarre units. However, let's find the mass in kilograms. So I need to know how many seconds there are in a year. And what the radius is in meters. I assume someone's looking it up. Or if not, let me know and I can look it up.
So for seconds, it's 31,536,000.
Seconds? Okay.
.496 times 10 to the 11 meters.
All right. And I suspect this stuff actually is on the front or back cover of the book. All right, so we have these numbers right here. We can plug in. So the mass of the sun is 1.496 times 10 to the 11th cubed over 31,536,000 squared times 4 pi squared over 6.67 times 10 to the negative 11th